So, I'm going to present my paper towards effective IoT, Internet of Things Management. This is the outline of my paper. I will start talking about the Internet, what was, what is, and what I believe it will be the Internet, and then I will talk about some requirements that I believe are important requirements in terms of Internet of Things management. I will start with the use of IP in the Internet, in wireless Internet of Things, and how can we take advantage of IP if, in fact, we want to use classical or standard IoT management protocols. Then I will talk about mobility. How can we support mobility? How can we support management in these very mobile environments? Then I will talk not only about security, but also with privacy. Then I will go to the fourth requirement concerning reliability. I believe that it is also a very important issue if we want to provide IoT management, because we need reliability. And I will conclude with how can we integrate human sensors and how can we provide management for these new environments that also has the human. And then I will also present you the platform that that we are using in my university to study some of these IoT management protocols. So starting from the beginning. Okay, we know that Internet is increasing, and in terms of the number of users, and it's also interesting because the Internet is increasing not only in the numbers of users, but also in the number of equipment that each user is connecting to the Internet. And lots of the equipments that are now connecting to the Internet communicate with each other without human intervention. In fact, we can apply things in Internet of Things in all aspects of our life, in smart buildings, smart cars, industrial automation, and so on. And I also believe that wireless sensors and actuators are important elements of the future Internet. And that can be critical if we want. The question is, how can we manage all of these thousands of devices that we are now connecting to the Internet? This is one of the architectures of Internet of Things. There are several of them. As you can see, we have here sensors and actuators. They are important elements. We have others architectures. Now, in terms of challenges, what do we have? One of the problems is the network size. How can we support management protocols in so small devices like wireless sensor and actuator networks? The energy well is the classical problem of wireless sensor networks. How can we provide energy efficient management protocols? Communication, because as you know, communication is the critical part and the issue that wastes more energy. We have also hardware limitations and dynamics. And dynamics, it's important because nowadays we have networks more dynamic when compared with the past. Why? Okay, thank you. Okay, we have now dynamics networks. Why? Because of the short lifetime of the devices, but also because of most of the devices that we are now connecting to the Internet are very mobile. So we have to provide IoT management protocols that support these dynamics. And self-configuration is also an important requirement for Internet management. Why? Because if in fact we have thousands and thousands of sensors connected, we have to find self-configuration plug-and-play mechanisms, because it's impossible to configure manually all of these thousands of devices. So it's important to find out how can we provide self-configuration mechanisms even in management. And I also believe that there is a gap, although there is a lot of research and a lot of work on Internet of Things. I believe that still's a gap between theoretical work and the use of IoT devices in more critical scenarios like health or like critical industries. And in my opinion, I think the reason for this difference between theoretical work and the use of IoT in real environments is related to these 5 topics. So I will try to analyze each of these 5 topics individually. So let's start with the use of IP in Internet of Things. Well, the first question is, why to use IP? Well, in fact, if we use IP, maybe we can use standard management IP protocols. Although we all agree that IP has a lot of limitation, it is a fact, returning to the first requirement, I was asking why to use IP in the new internet, in the Internet of Things. Well, the question here is maybe we can take advantage of IP if in fact we want to use classical management protocols. We all agree that IP has a lot of disadvantages, but it is a fact that IP is the common language that every device speaks. So if we can take advantage of this common language IP, I think we can have several advantages. So the problem is that TCP IP stack is too complex to be used directly in those devices that are energy limited. On the other hand, the problem of addresses. We do not have enough addresses if we want to assign an address to all of these IoT devices that we are now connecting to the internet. The third problem is the overhead. If I have a sensor that is monitoring my heartbeat, maybe I only need 4 or 5 bits to send that information. So why to add an overhead IP header of 60K of overhead? So in fact, it is an advantage to use IP, but we have to find a different approach if in fact we want to use IP directly in IoT devices. And what about IPv6? As you know, IPv6 has several advantages when compared with the IPv4. One of the advantages is the larger address space. If we use the 128-bit addresses of IPv6, well, compare it with the 32-bit addresses of IPv4, maybe we have enough addresses to assign an address to all of these IoT devices that we are now connecting to the internet. There are other properties like mobility, security, are now native in IPv6. But although IPv6 is simpler when compared with IPv4, the header is bigger. And the header is bigger because we have the source and destination addresses that are now, as I said, 128-bit addresses. So we need to find solutions if in fact we want to take advantages of IPv6. And we have also anycast address. Anycast address is an interesting property of IPv6 that can be used to combine classical IP addresses with the geographic and location addresses. There are already some work on these topics. In the past, the IETF group created the 6LoWPAN. The idea of 6LoWPAN is to use IPv6 using compression methods, so that the overhead is, we need to compress the header, so the overhead be minimum when compared with the original IPv6 headers. And there are operating systems that support the use of IPv6 or 6LoWPAN directly in devices like wireless sensor and actuator networks. Here we have the traditional approach when we integrate the IP world with the wireless sensor network. We have a gateway where it works like a firewall. And in this second scenario, we are using IP directly in all the devices. And in these cases, maybe we can use directly the traditional IP management protocols. But in fact, if we want to use traditional management protocols directly in IoT devices, it's not only a problem of overheads, it's not only a problem of energy. There are important differences between these two worlds that we need to overcome. These tables presents some of these differences. As you see, for instance, IP networks, classical IP networks are application independent. Low power devices networks are application specific. We use cross-layer mechanisms. Routing are address centric, based on IP addresses in IP networks, and several times routing is data and location centric. For instance, if we have sensors in the forest and the fireman wants to know the temperature of a specific part in the forest, it doesn't matter if the query message goes to sensor A or to sensor B. The important is that one of the sensors in that specific part of the forest answer to the fireman. Data flow usually is one-to-one in IP networks, and in low power devices, many of the time is many-to-one. Data rate is high in IP networks and is low in low power devices. The classical problem in IP networks is bandwidth. The classical problem in low power devices is energy. We don't have problems with the lifetime in in classical IP networks. We do have in low power devices networks. So these are important differences that we must overcome if in fact we want to use IP directly, even in those very small IoT devices. But as I said, that can be an important advantage to use classical management protocols. Now let's go to the second requirement, mobility. And the question here is, can we use standard IP management protocols in these very mobile environments? How can we support management with all of these mobile devices? And in fact, if we analyze the state of the art, most of the work on IoT management are based on static environments. And the question is, how can we support, how can we translate this work to mobile environments? Another issue related to mobility is device and service discovery. It's, as I said before, it's very important that if we can provide solutions for all of these thousands of devices that are now connected to the internet, because it's impossible to configure manually all of them, all of these thousands of devices. So it's important to find automatic solutions. I think there are two different types of approaches. We have what I call you catch me approach, when it's very similar to Wi-Fi, where the sync node broadcast messages, so that when a mobile node or a new node arrives to the network, it can detect these broadcast messages and can initiate the registration procedure. The problem of this approach is that those devices that are already registered in that network also receive these broadcast messages, so they also waste energy. So I think we need to look to what I call I catch you approaches. And the idea is the responsibility to send the beacon messages announcing itself that it is now in the network, is the responsibility is of the node. And using this approach, we can save energy. The third approach is related with security and privacy. And the question is, if in fact we are using IoT management protocols, we need also to support security and not only security but also privacy, because we do not want to create a big brother. And let's go to the fourth requirement, reliability. As I was saying before, if you use Google to find papers about IoT in critical scenarios, you only find a few papers. Sorry, I'm telling not what. If you use Google to find papers about IoT in critical scenarios, you will find thousands of them. But if you try to use Google to find critical scenarios that use reliable solution, it's more difficult. And as I told you, I think the reason for this gap between academic work and practical work is concerned with reliability. If we provide reliable solutions, I think we can overcome this gap and start using IoT even in critical scenarios like in industries. In the past, we have a European project that where we developed critical MAC protocols so that we can use wireless sensor networks in these critical scenarios. And the industry where we test our solution to check if in fact we could provide reliable solutions was a refinery. The idea is to compare the use of classical sensors, cabled sensors, with our solution based on wireless sensor networks with reliable protocols. If at the end we can provide with wireless sensor networks so reliable solutions as they are with cable solutions with the classical approach, in fact we are offering solutions to start using IoT devices like wireless sensor networks in very critical scenarios. So the question here is also how can we provide IoT management, a reliable IoT management. Now let me talk about the fifth requirement, the human in Internet of Things. And it is also important because nowadays humans carry a lot of sensors with him. The human uses the smartwatch, Google Glasses, the smartphone has a lot of sensors, and it's interesting to see how can we manage all of these sensors that humans transport with him. This slide presents the boxes that we must take care if in fact we want to provide IoT management, if we include the human in the new internet. And I think I have 3 minutes. More? 6 minutes. Okay, perfect. Okay, now talking about general IoT management, as I told you, the question here is how can we provide management with all of these requirements, okay? If we analyze the state of the art, we see we have two important groups of solutions. We have those solutions by IETF, like RESTCONF or CoMI, the CoAP Management Interface, and we have another important solution by Open Mobile Alliance, OMA, and it is the lightweight machine-to-machine protocol. In general, the management protocols need to support monitoring of network status. They need to detect faults, they need to configuring operating parameters, and to gather information on network performance. But as I said here, we are now facing a new internet. We do not have only traditional devices, but we have now constrained devices. We have now very mobile environments. We have human sensor humans in the internet. So the question is, in fact, how can we provide management of all of these things? According to ITUT recommendations, there are several components like the manager, the agent, the gateway manager, and the client. But ITU does not provide a specific structure for device management protocols. So if we analyze the proposals by IETF, we have the first one, the SNMP, that was proposed in 1988, but it is not very efficient to these low power devices. Later, IETF proposed the NetConf, Network Configuration Protocol. And it is interesting because the NetConf can interoperate with SNMP. And in 17, the IETF proposed the RESTCONF. RESTCONF does not intend to replace NetConf, but offer an HTTP interface that is compatible with NetConf. We have also the lightweight machine-to-machine protocol proposed by OMA, the Open Mobile Alliance, and is very simple. It uses a client-server architecture. In this slide, we have a comparative table where we can see some of these management protocols. The information that they use, the language that they use, the transport protocol that they use. And here we have also a table with some commercial solutions that use these protocols. Now in these 2 minutes, let me present you some of the platforms that we are working on and where we are evaluating some of our IoT management protocols. In general, we have been working with industries. We have a Portuguese project where we are evaluating and promoting the use of 5G, and we are also evaluating some management protocols. And we have also using a platform that I'm going to present you now that is not related to industry, neither to telecom. One of the problems that we face in academia, in our university, is every time that we have a project with industry, it's very difficult well, we have our lab test beds, but when we want to evaluate our protocols in the field, it's very difficult. So it was important to us to have a real platform in our university. So one day I read this paper from Dartmouth University, and I used as a starting point to create our platform called ISABELA. ISABELA is an Internet of Things student advisor, and we call Internet of Things student advisor and best lifestyle analyzer. The idea is to use the sensors from the smartphone and the sensors from the environment, and to analyze the physical and emotional parameters of the student and the physical parameters of the environment. And if we combine all of this information, we can know if the student is too stressed, if the student attends the classes, if the student is tired, if the students do not sleep well. And the idea is in real time to advise the student so that it can get good performance results. And this academic platform is interesting by itself, but it is also important because we are using this platform to evaluating some of IoT management protocols. We are using and evaluating the lightweight M2M protocol. We are using Lesson and Fireware, and I think, yes. Just to conclude, this is the ISABELA, and it is here that we are evaluating some of these protocols. Okay, just to conclude with this slide with the timeline and the challenges of IoT management. And to conclude, I should say that, in fact, this is a very important area, and we need to find management protocols that can overcome all of these issues that I presented. Okay, thank you very much.
Thank you.